Hi guys, welcome to Amateur Chemistry. So in today's video I will be making the dangerous but incredibly beautiful halogen bromine, and I know that there is already a ton of good YouTube videos on it, but I need it for a big project I am currently working on, and I thought that it would be nice to show you just how beautiful this element is. Bromine along with mercury are the only chemical elements that are liquid under standard conditions, and that makes them very unique. However, they are rather dangerous, and while mercury is pretty safe by itself, as I showed in a previous video by touching some of it, bromine on the other hand is extremely hazardous in its pure form. However, it isn't as toxic as mercury, because when it's in a compound it's quite safe, unlike mercury, which forms compounds that are toxic as nuts. Bromine is also tremendously useful in chemical synthesis. It's the go-to halogen for a lot of reactions because it has a moderate reactivity compared to, for example, chlorine or fluorine. It is also a liquid, and since almost all organic syntheses are carried out in the liquid state, bromine is just perfect for them. It also looks incredible in an element collection, and I actually already have this small ampule of it. To make it, I used the classic method involving making chlorine from pool tablets and displacing the bromine with it. This method is really simple and fine for making a sample for an element collection, but for chemical synthesis it has a few problems. The first one is that for my project I will need bromine in large quantities, and it is really difficult to scale up this method. The second issue is that there is chlorine present, which can actually react with the bromine to form an interhalogen compound that slightly contaminates it. Like I said, for most applications it is fine, and it doesn't change the appearance or physical properties of the bromine in any way, but for a complicated chemical synthesis, the bromine has to be really pure, and any chlorine can completely screw things up. That's why I have to make my bromine in a different way than everyone. I also have to make a pretty substantial quantity of it, so finding a good method was really difficult. After some research, I came across a route that should produce a lot of pure bromine, but it has the slight drawback of using an extremely explosive and incredibly dangerous compound, which is manganese heptoxide. As you may know, it's this green oil that is so oxidizing that touching it with something like a blade of grass can very rapidly decompose it, and this property is actually what I want for my bromine synthesis. You see, I will be starting from a compound called potassium bromide, which I like to imagine as a level 2 of table salt, and to rip apart something like table salt, you need a ton of oxidizing power. The manganese heptoxide method also can't contaminate the bromine in any significant way, and involves the use of pretty basic reagents, so it will be just perfect for me. There are also some safer ones, like the one involving sodium persulfate or hydrogen peroxide, but I went with the heptoxide one, because for me it seemed the most fun and accessible one, and it is said to have a pretty high yield, which will save on the expensive potassium bromide. Anyway, to start I have to measure out the ingredients, and as the first one I obviously need some potassium bromide. Over some time I managed to accumulate a pretty big amount of it, some of which was provided by an online chemistry supply store, BM Chemistry. BM Chemistry sells a lot of hard-to-get reagents along with laboratory equipment and lots of other things, so you can check out their page, to which there is a link in the description. Anyway, I measured out 375 grams of potassium bromide and added 100 grams of a chemical called potassium permanganate to it, which is this beautifully purple oxidizing agent, and when I later combine it with some sulfuric acid, it will allow for the creation of manganese heptoxide. I mixed the reagents and transferred them into a 2-necked flask. I also added about 150 ml of distilled water into the mix to create this thick black slurry and assembled this very neat distillation apparatus. It will allow me to condense the bromine vapors as they form and collect the bromine in this ice-cooled flask, and since its vapors are very reactive and tend to escape from everything, I had to grease all the joints, but I couldn't use my good old engine grease, and instead I used some concentrated sulfuric acid, which in this case works very well as a grease. Also, even though I used some very cold water to condense the bromine and cool down the receiving flask, some of its vapors are still going to escape, and that's why I built this inverse funnel trap filled with a sodium thiosulfate solution, which will neutralize most of them, prevent suckback, and most importantly, help preserve my fume hood because bromine vapors can completely obliterate plastic tubing. Anyway, to start the reaction, I attach an addition funnel to the flask and filled it with 145 ml of 96% sulfuric acid drain cleaner, and before starting the addition, I realized that my flask was a little too small to contain everything, but it just so happens that I don't have a bigger one, so I just prayed to the chemistry gods to make this work and started the sulfuric acid addition. Immediately after the first drops of sulfuric acid hit the mixture, a lot of orange bromine vapors started rising from it. At first they didn't distill over because bromine can dissolve into the water, giving it this red tint, but when its solution gets saturated, the vapors start climbing up the apparatus and condense in the ice-cooled condenser. As the pressure inside the apparatus increases, some of the bromine vapors escape and end up in the trap, which does a good job of neutralizing them, but to be absolutely safe, I had my fume hood running all the time. After some time, a lot of bromine started coming over into the receiving flask, which looked really nice, and I stared at it for way too long. I continued this sulfuric acid addition, and just the heat from the reaction alone was enough to make all the bromine vaporize, which is good because I didn't need to use any external heating. Okay, and now it's time to explain the reactions going on here, and honestly, I couldn't find any good info about some of them, but I will try to explain everything as best as I can, so that you can get a hold of the overall process. Okay, so one of the first reactions going on here is the formation of hydrogen bromide from sulfuric acid and potassium bromide. It normally is a gas, and that means that it could easily escape the apparatus, but since there is water present, it dissolves into it, forming hydrobromic acid. Simultaneously, sulfuric acid attacks the potassium permanganate and turns it into permanganic acid, which is then dehydrated to form the infamous manganese heptoxide. If this process happened in a dry environment, it could very easily lead to an explosion, since manganese heptoxide decomposes at just 55 degrees Celsius. But similarly to the hydrogen bromide, the water also makes everything work here by allowing the manganese heptoxide to immediately react with the hydrobromic acid to produce bromine, which quickly evaporates because all these reactions produce a lot of heat. Okay, so this explanation is the best I could come up with, but as I said, I couldn't find much information about some of the reactions, so a lot of this is just speculation, and you can feel free to correct me in the comments. Also, in the end, all the reaction equations don't really matter here, because bromine is being produced, and even if there is some dark chemistry voodoo magic involved in this, I won't question it. Also, before I get a lot of comments asking about this, you can run this reaction with sodium bromide, and you can use dilute drain cleaner acid. You can even substitute potassium permanganate with manganese dioxide that you can get from some batteries. But if you don't want to hurt yourself or your neighbors, please don't try making bromine yourself. Okay, now back to the reaction. After a few hours, I have collected quite a bit of bromine in my receiving flask. An overflow did also happen when I wasn't looking, and some of the reaction mix got onto the bromine, but this shouldn't be a problem since I will carry out a few cleaning steps later. Anyway, when the dripping funnel ran out of sulfuric acid, I added some more for good measure, and after a few more hours, the reaction seemed to be nearing completion. In the receiving flask, there was a really nice amount of bromine, which I felt was good enough, so I let everything cool down and started disassembling the apparatus. A ton of bromine vapor escaped from it, but it was thankfully quickly picked up by my fume hood, and in the end, I was left with a good amount of some impure bromine. To clean it up, I first have to remove the upper water layer, and I can do that using a separatory funnel. After double checking that the valve is closed, I poured in the dirty bromine, which thanks to all the vapor, looked really scary. I then drained it into a beaker and now it looked much better, however it was still a little wet, so I got it back to the separatory funnel and poured in roughly a third of its volume in concentrated sulfuric acid, which should hold on to any remaining water. It actually sat on top of the bromine, and that felt really weird, because it's a very dense liquid, but it turns out that bromine is even denser, being more than 3 times as dense as water. I washed the bromine by gently shaking it with the sulfuric acid, and frequently venting the funnel to prevent a disaster. When I was done, I got the no dry bromine into a flask, and before purifying it further, I had to do everything again. That's because for my project I need heaps of bromine and I couldn't make it all at once because of the size of my flask, so I decided to do it into portions, and for the second one I repeated exactly what you've just seen, so I won't bore you with the details. In the end, I was left with around the same amount of acid-washed bromine as before, so I combined it with the first batch, which has been chilling outside for the past day in this contraption made to prevent the bromine from escaping, and now I have a decent amount of some pretty pure bromine. It's really weird to shake it around because it's really dense and it feels kind of similar to mercury. Anyway, now I have to clean it one last time because even though it's mostly water-free, it still has some sulfuric acid in it, which I have to remove by distillation. What's funny is that I am doing all this in my parents' garage, so I am exactly like Nael read a few years ago, and I am really scared that something will go wrong during the distillation. However, I can't turn back now, so I assembled my distillation setup once again and started to gently heat the bromine. Fortunately, it didn't boil too vigorously, and the distillation went pretty smoothly, and if I don't think about all the potential disasters it might cause, it looks just incredibly beautiful. The boiling and condensing bromine is just very mesmerizing to watch, and it looks like some weird alien blood. The whole distillation is also quite fast, and in about 2 hours all the bromine came over to the receiving flask, leaving behind a few drops of sulfuric acid. I let everything cool down and disassembled the apparatus, and in the end I was left with half a flask of extremely pure bromine. When it comes to the yield, I managed to get 382 grams of it, which corresponds to a percent yield of around 75%, which is very good and will be plenty for my project. However, before using all the bromine for it, I got about 20 grams of it into a vial to do some experiments with. As the first one, I wanted to do the classic reaction of bromine with aluminum, so I got some aluminum foil into a test tube and poured in some bromine, which quickly reacted to form aluminum bromide and a lot of this nice deadly smoke and sparks. This reaction also demonstrates that bromine should never be kept near aluminum, because it can end very badly. When the reaction finished, I put the test tube into some water to dissolve the aluminum bromide and recover this nice small ball of pure aluminum that melted from the high heat of the reaction. For the next experiment, I want to show you just how quickly bromine evaporates, so I put a small amount of it onto a petri dish, and after a few minutes of producing copious amounts of vapor, it was gone. Bromine vapor is really heavy and tends to accumulate on floors of rooms, destroying everything in its path. It also smells pretty bad, similar to chlorine, and this smell is actually the reason for the name bromine, which came from the Greek word bromos, meaning stench. Since bromine's vapor is so heavy, it can be poured similarly to a liquid, and I can easily fill a beaker with it. Also, despite bromine being very reactive and dangerous, it is not too toxic for your skin, and for science, I put my hand into its vapor and felt the heat of my hand being brominated, which was quite terrifying, but in the end I was completely fine. Also, to easily neutralize bromine or its vapor, a chemical called sodium thiosulfate can be used, which reduces the bromine, making it way less dangerous, and you can see this in action in this beaker. It's worth noting, however, that this produces small amounts of elemental sulfur that can be a nightmare to remove from glassware. Another interesting property of bromine is that it can dissolve in water to form this orange liquid that in some cases can be used as its substitute. It also dissolves readily in organic solvents, and this form is often considered to be a little bit safer to work with than pure bromine. After all the experiments, I was still left with about 15 grams of bromine in the vial, and I couldn't store it for long because the bromine already started eating through the plastic cap. It does this to almost every conventional mean of storage, so to prevent it from escaping, I sealed it in a glass ampule made from a test tube, which will hopefully allow me to store it for a long time. Anyway, I hope that you guys like this beautiful project, and thank you very much for watching. Like and subscribe if you enjoyed the video. Also, as always, big thanks go to my patrons, especially Isaac Von Liu, Dangerous Lab, Adam Fowler and T. Handley. as well as R2D2, Rairi Refogul, Joseph Cudi, MI, William Bragely, Dew Nitrate, Mismatch Scientist, and Monia Guralik. If you would also want to support my work and gain access to exclusive content, you can consider becoming a Patreon, and see you guys in the next video.